Welcome to the sixth session of this exponential and logarithmic functions series. In this session, we will continue to level up our understanding and skills using more advanced techniques to solve exponential and logarithmic equations and inequalities. Hello, math champions! I'm Dr. Chen. If you want to improve your math skills and understanding, so that you gain confidence, enjoy math more, and get better results, click subscribe and hit the notification button so that you don't miss anything. Welcome to the sixth session of this exponential and logarithmic function series. In this session, more advanced techniques of solving exponential and logarithmic equations as well as inequalities are demonstrated through 8 worked examples. In example 1, based on the linear relation of 2x plus 5y equals 20, where both x and y are positive real numbers. The question is to find the maximum value of common logarithm of x plus common logarithm of y. Since 2x plus 5y equals 20, both sides of the equation can be squared, and we have 2x plus 5y, or in parentheses squared, is greater than or equal to 40xy after simplifying the expression. Because 2x plus 5y, or in parentheses squared, equals 400, we have the inequality of 40xy is less than or equal to 400. Hence, xy is less than or equal to 10. Now, after taking the common logarithm on both sides of the inequality, we have the inequality of common logarithm of x plus common logarithm of y is less than or equal to 1. Therefore, the maximum value of common logarithm of x plus common logarithm of y equals 1. The question in example 2 is to find the minimum value of 1 over x plus 1 over y, given that the common logarithm of x plus common logarithm of y equals 2, where both x and y are positive real numbers. Since common logarithm of x plus common logarithm of y equals 2, common logarithm of xy equals common logarithm of 10 squared. Hence, xy equals 100. Since both x and y are positive real numbers, 1 over x plus 1 over y is greater than or equal to 2 times square root of 1 over xy, which equals 2 times square root of 1 over 100, which equals 1/5. Based on the above, the minimum value of 1 over x plus 1 over y equals 1/5. Example 3 presents an exponential function fx which equals 3 to the 2x minus k plus 1, or in parentheses times 3 to the x plus 2, where x is a real number. The question is to find the value range of k that enables fx to be greater than 0. Since the exponential expression can be reduced to its quadratic form, so in order to enable its quadratic form to be greater than 0, we need to discuss the situation whether the discriminant of this quadratic form is greater than or equal to 0, or it is less than 0. So, when the discriminant, which equals k plus 1, or in parentheses squared minus 8, is less than 0, obviously, in this situation, fx is greater than 0. After solving the inequality, the value is between negative 2 square root 2 minus 1 and 2 square root 2 minus 1, excluding both endpoints. When the discriminant is greater than or equal to 0, the value range of k obtained in this scenario is less than or equal to negative 2 square root 2 minus 1, or is greater than or equal to 2 square root 2 minus 1. Since 3 to the x is always greater than 0, so if 3 to the x sub 1 plus 3 to the x sub 2, which equals k plus 1, less than 0, fx will greater than 0. Therefore, k plus 1 is less than 0 will intersect with the inequality k is less than or equal to negative 2 square root 2 minus 1, which result in k is less than or equal to negative 2 square root 2 minus 1. In summary, when k is less than 2 square root 2 minus 1, fx is greater than 0. Example 4 presents a function fx equals x squared plus c, while the composite function f of fx equals f of x squared plus 1. Based on that, there are two questions follow, and the first one is to find the expression of gx, given that gx equals f of fx. The second question is to find the value range of lambda, so that the function phi x equals gx minus lambda times fx is a decreasing function when x is less than negative 1, and phi x is an increasing function when x is between negative 1 and 0. As for the first question, since f of fx equals f of x squared plus 1, so f squared of x plus c equals x squared plus 1, or in parentheses squared plus c. Hence, the value c is obtained, which is 1. Therefore, gx equals x squared plus 1, or in parentheses squared plus 1, which equals x to the 4th plus 2x squared plus 2. After finding the expression of gx, we come to question 2. So we have the expression of phi x equals x to the 4th plus 2x squared plus 2 minus lambda times x squared plus 1, all in parentheses. After being rearranged, phi x can be rewritten to its turning point form by adding and subtracting the term of 2 minus lambda over 2, or in parentheses squared, as it can be seen on the screen. Here we continue to work on question 2 of example 4. After phi x being written in its turning point form, we find that phi x is an even function, because phi negative x equals phi x. So, phi x is symmetric to y-axis, which means that phi x decreases when x is less than negative 1 is equivalent to phi x decreases when x is greater than 1. Similarly, phi x increases when x is between negative 1 and 0 is equivalent to phi x increases when x is between 0 and 1. Hence, as long as the axis of symmetry x equals 2 minus lambda over 2, which equals negative 1, the phi x satisfies the requirement. So, after solving this linear equation of 2 minus lambda over 2 equals negative 1, we find that lambda equals 4. Hence, when lambda equals 4, phi x decreases when x is less than negative 1, and phi x increases when x is between negative 1 and 0, excluding both endpoints. Example 5 presents the logarithmic function fx equals logarithm base 3 of open bracket x squared minus 4mx plus 4 times m squared plus m plus 1 over m minus 1, close bracket, where m is greater than 1. There are two questions in example 5. The first question is to find the minimum value of fx. The second question is to prove that the minimum value of fx is no less than 1. As for the first question, we transform the base argument of the logarithmic expression to its turning point form so that we have fx equals logarithm base 3 of open brackets x minus 2m, or in parentheses squared, plus m plus 1 over m minus 1, close bracket. According to the turning point form, when x equals 2m, fx reaches its minimum value, which is logarithm base 3 of the result of m squared minus m plus 1 over the result of m minus 1. As for the second question, based on the expression of its minimum value, logarithm base 3 of m plus 1 over m minus 1, or in parentheses can be written to logarithm base 3 of open brackets m minus 1 plus 1 over m minus 1 plus 1, close bracket. Since m is greater than 1, m minus 1 plus 1 over m minus 1 is greater than or equal to 2. Hence, the minimum value of fx is greater than or equal to logarithm base 3 of 3, which is 1. Example 6 shows the quadratic equation ax squared minus 4ax plus 1 equals 0, where alpha and beta are the two positive real roots of this quadratic equation, and they satisfy the inequality of modulus of common logarithm of alpha minus common logarithm of beta is less than or equal to 1. The question is to find the value range of a. Since the modulus of common logarithm of alpha minus common logarithm of beta is less than or equal to 1, common logarithm of alpha over beta is between -1 and 1, including both endpoints. Hence, both alpha over beta and beta over alpha are between 1 over 10 and 10. On one hand, alpha over beta plus beta over alpha reaches its maximum value, 101 over 10, when alpha over beta equals 10 or equals 1 over 10. On the other hand, alpha over beta plus beta over alpha is greater than or equal to 2. Therefore, the value range of alpha over beta plus beta over alpha is between 2 and 101 over 10, including both endpoints. According to the Vieta theorem, alpha plus beta equals 4, while alpha times beta equals 1 over a. Hence, alpha over beta plus beta over alpha equals the quotient of the result of 16 minus 2 over a to 2 over a after being simplified. Then this simplified expression is between 2 and 101 over 10, including both endpoints. After solving these inequalities, we find the value range of a, which is between quarter and 160 over 121, including both endpoints. The given criteria in example 7 are that a is greater than b and b is greater than c, which is greater than 0. Here m is greater than 1. The question is to find the value range of lambda so that the logarithm base a over b of m plus 2 times logarithm base b over c in parentheses squared of m plus 4 lambda times logarithm base c over b in parentheses to the fourth of m is greater than 0, where lambda is a real number. To answer this question, we need to transform and simplify the left-hand side of the inequality, which equals 1 over logarithm base m of a over b plus 1 over logarithm base m of b over c plus lambda over logarithm base m of c over a. Since the expression is greater than 0, we have lambda over logarithm base m of c over a is greater than -1 over logarithm base m of a over b minus logarithm base m of b over c, which can be transformed to lambda over logarithm base m of c over a is greater than 1 over logarithm base m of b over a plus 1 over logarithm base m of c over b. To simplify the process, we here assume p equals logarithm base m of b over a, which equals logarithm base m of b minus logarithm base m of a. Similarly, we assume q equals logarithm base m of c over b, which equals logarithm base m of c minus logarithm base m of b. So in this way, we can see that p plus q equals logarithm base m of c minus logarithm base m of a, which equals logarithm base m of c over a. Here we continue to work on example 7. Since m is greater than 1, c over a is greater than 0 but less than b over a, which is less than 1. So logarithm base m of c over a equals p plus q, which is less than 0. Hence, lambda over logarithm base m of c over a is greater than 1 over logarithm base m of b over a plus logarithm base m of c over b, which leading to lambda over the sum of p and q is greater than 1 over p plus 1 over q. Hence, after being simplified, lambda is less than p over q plus q over p plus 2. Since p over q plus q over p plus 2 is greater than or equal to 4, we may conclude here that lambda is less than 4. Example 8 shows a function fx equals logarithm base a squared minus 1 of x squared minus 2x plus 3 is greater than negative 1. The domain of the function is between 0 and 3, including both endpoints. The question is to find the value range of a. To solve this question, we need to rewrite the logarithmic base argument to its turning point form, which is x minus 1 or in parentheses squared plus 2 using computing square method. Based on the given domain of the fx, the base argument is between 2 and 6, including both endpoints. At this point, we need to discuss the value range of a in regard to the logarithmic inequality. When a squared minus 1 is greater than 1, due to the value range of the base argument, the function is greater than 0, which is of course greater than negative 1. Therefore, when a is less than negative square root 2 or greater than square root 2, the function fx is greater than negative 1. When the base a squared minus 1 is between 0 and 1, which is equivalent to a is the union of the real set from negative square root 2 to negative 1 with the real set from 1 to square root 2, due to the base argument is a closed real set from 2 to 6, logarithm base a squared minus 1 of 6 is less than logarithm base a squared minus 1 of 2. So we just focus on the smaller number, and if it is greater than negative 1, then fx will be greater than negative 1. So we need to solve the inequality logarithm base a squared minus 1 of 6 is greater than negative 1. After simplifying the logarithmic inequality by applying the logarithmic laws, we have the final form of logarithm base 6 of a squared minus 1, or in parentheses less than -1, which is equal to negative logarithm base 6 of 6. Hence, we obtain the result of a for this logarithmic inequality. A is less than negative square root 7 over 6 or greater than square root 7 over 6. Here we continue to work on example 8. So when the logarithmic base is between 0 and 1, a is between negative square root 2 and -1, or between 1 and the square root 2. And the value range of a we obtained is less than negative square root 7 over 6 or greater than square root 7 over 6. After being intersected, the value range of a under such circumstances is between negative square root 7 over 6 or greater than square root 7 over 6, excluding all the endpoints. Hence, we may conclude that the value range of a which satisfy the inequality f(x) is greater than -1 is less than negative square root 2 or between negative square root 42 over 6 and -1, or between 1 and square root 42 over 6 or greater than square root 2. Very long expression, excluding all the endpoints, of course. If you enjoyed this video, please give it a thumbs up and subscribe to help me make more math content like this. I will see you in the next video.